It's my pleasure to welcome you to our final morning of Standard Model at 50. We start before the coffee break with 3 talks on new developments, part of our desire to look both backwards and forwards during these 4 days. Our first speaker, Dr. Jurgen Schukraft, is a senior researcher at CERN. He asked me to keep his introduction as brief as possible so that he could have more time to talk, and I promised I would do so. So if you want to know more about him, there's always Google. He will discuss the Quark-Gluon phase transition. Dr. Schukraft.
Actually, new is relative. Ultra-velocity heavy ion physics is an offspring of the Standard Model, but we did have our 30th anniversary 2 years ago. Ultra-velocity heavy ion physics was born in the fall of 1986. Yes, so in the fall of 1986, so 68 reversed, when we had first beams actually of light ions, of oxygen ions at both CERN and Brookhaven. Now this event was announced by CERN in a press release, as was already the use at these days, with the usual hype, world record in energy, breaking new grounds. But unlike many press releases, this one did have some useful information. We can find that there are up to 400 particles created per collision, and that over 300 physicists were looking busily over the data to see whether the famous Quark-Gluon Plasma really has been achieved. Now, you would have thought with almost 1 physicist per particle, they would have figured that one out quite quickly. But it actually did take many years. It was much more complicated, but also much more rewarding. And so I will, in this talk, try to give you some highlights from these first 30 years of heavy ion physics, reminding you what it is really all about. Voila, that looks better. Showing you some of the tools from accelerators to theory. Give a very few of the highlights from the results, and at the end, if time permits, a few words about the future. So heavy ion physics are messy. You see here one of these streamer chambers pictures with many particles. Why would you do that? Now, I learned yesterday that Weltmann probably would have loved these collisions because he liked particles who make click in a detector. And there are many clicks for the bang. But an even better reason was given by T.D. Lee 10 years before the first collisions. He observed that in elementary collisions, you concentrate the energy in a small volume to create high-mass particles like the Higgs and to measure short-distance phenomena. In AA, he observed we distribute the energy over a large volume, and so he said we can study bulk phenomena and the structure of the vacuum. So this is QCD in the long wavelengths, large volume, many body limit, actually in the regime where the strong interaction really is strong. More concretely, we want to measure the phase diagram of strongly interacting matter shown here with the temperature and the density axis. So if you either compress matter like in a neutron star or you heat it like in the early universe, QCD predicts that there is a new state of matter, the Quark-Gluon Plasma, where the hadrons are deconfined, so there are no bound states, and where chiral symmetry is approximately restored, so the quarks, the light quarks at least, are approximately massless. So in the 1980s, the expectation was that that would be a weakly interacting, almost free ideal gas of quarks and gluons. We, on the experimental side, were a bit less dogmatic. Our idea was to smash things as hard as we could and just see what happens. Now, this plot you've seen already before in a version by Carlo, the Livingston plot, which shows the center of mass energy versus the first year of operation for some of the high energy machines which were important for the Standard Model, and you see this exponential increase in energy with a doubling time of about 4 years. The doubling time in heavy ion physics was actually even more impressive, rivaling Moore's law, which was of course only possible because we would reuse the machines built by high energy physics over a much longer time scale. The only machine built for heavy ion physics is this RIG collider at Brookhaven. So we could span 4 orders of magnitude in energy in 30 years, and at the same time the field grew from a few dozen physicists into over 3,000 people active worldwide today, really moving from the periphery of nuclear physics into one of its central activities. If you watched this plot carefully, you may have seen that the LHC actually is slightly late as a high-energy machine, but it's perfectly on time as a heavy ion collider. Now, like the accelerators, also the first generation of experiments, we made big use of the scrapyard of high-energy physics and built the experiments using a lot of existing equipment, including, for example, the streamer chamber. And this was because the first set of the program, which was approved at CERN in the mid-80s, with light ions, was really meant as an exploratory program to see whether we can measure these high multiplicity interactions, whether we can analyze them, and whether they are interesting in the first place. Now, with these questions answered to the affirmative, we had a second generation of experiments when LED beams finally became available in the mid-90s. And these were dedicated special purpose experiments, each of them specialized for a certain observable, hadrons, muons, or lepton pairs, for example. Finally, with RIG, we first saw the first generation of really general purpose heavy ion collider detectors. They were called STAR and Phoenix. And finally, in 2010, the LHC came online. As you know, the LHC, about for 4 years every year, turns from a large hadron collider into a collider of large hadrons. Here you see the collision of two lead ions. We have one dedicated heavy ion experiment, the ALICE experiment, which in very good heavy ion fashion makes use of leftover equipment from high energy physics. We are using the L3 magnet of Professor Ting. But also ATLAS, CMS, and even LHCb are participating fully in the heavy ion program. Okay, let's come to the final kit in our toolkit, and that is theory. You see here a state-of-the-art calculation from the lattice of the equation of state. So the energy density or the pressure as a function of temperature. We have actually learned over time from the lattice that there is no phase transition. There is actually a smooth crossover between hadron gas and the Quark-Gluon plasma with a critical temperature, or rather pseudo-critical temperature, of about 155 MeV, corresponding to an energy density of half a GeV per cubic Fermi. This is actually not very much above normal nuclear matter. It's only about twice the energy density in a proton, or 3 times the energy density in a nucleus. Of course, we use a lot of perturbative QCD to calculate cross-section and dynamical coefficients. We use phenomenology, hydrodynamic, thermal models, and event generators. Duality, which was mentioned by David yesterday, conformal field theory in anti-de Sitter space made an unlikely appearance in heavy ion physics. It found some applications, and I will discuss some of them later on during my talk. And finally, there's another first principles approximation of QCD, this time in the classical high density limit called color glass condensate, which we make use of in particular to calculate initial conditions, what happens at the moment of collision or before, a theory which also used otherwise, for example, in small x physics. Okay, let's finally come to some results. I will show you results which are relevant for chiral symmetry restoration, deconfinement. I will show you some of the properties we have measured with this Quark-Gluon plasma, and at the end come to one of the surprise discoveries made at the LHC. So chiral symmetry restoration is linked to the value of the quark condensate. You see here again a lattice calculation of the quark condensate as a function of temperature. And it's thought that the mass of hadrons in medium at high temperature that is related directly to the value of this condensate. This is shown here in the case of the rho. If we are in the vacuum, meaning a high value of the condensate, you have the vacuum rho. And then if we increase the temperature, it is thought that the rho either changes its mass in proportion to the condensate, or maybe also just gets broad, the spectral function disappears. So which of the two, if any, is true? For this, we have measured lepton pairs in heavy ion collisions in the region of the rho. You see the rho, that's the expected shape and amount, is nowhere to be seen, nor do we see its mass-shifted cousin. What we see instead is a rather broad continuum with some leftover rhos. So indeed, it looks like the rho, when the chiral condensate melts, when the chiral condensate goes away, does change its spectral function. It becomes broad. It has to reunite with its chiral sibling, the A1, but that we have not yet found. And so this is thought to be a sign of approach to chiral symmetry restoration. If you now look at the high mass part of this spectrum on a logarithmic scale, you see that this is a beautiful exponential spectrum, e to the minus m over t. And if you can relate the slope of these lepton pairs directly to the initial temperature of the Quark-Gluon plasma, and you find about 250 MeV. Now this is much, much higher than the value you heard just before from lattice QCD, so we really should be very deep inside the plasma. Incidentally, the yield of these, not the slope, but the yield, tells us how long the Quark-Gluon plasma shines. So it tells us the lifetime of the system, which turns out to be about 6 to 7 Fermi over C. Of course, this sounds very short, but it's not what the absolute time which counts, but this is many relaxation times, so really we seem to have a thermally radiating, long-lived system. Now, the story of deconfinement is less straightforward. It's more tortured, actually. It was famously predicted just before we had the first collisions by a famous paper as a smoking gun, as a well-calibrated signal of the Quark-Gluon plasma. The idea is very simple. You take a bound state, like the shape psi, you put it into a deconfining medium, and it will melt, it will be suppressed. This is borne out by lattice QCD, where you see the heavy quark potential at 0 temperature, the linear rise, the confining potential. This potential is screened at increasing temperature, and so bound states can no longer exist and will decay. Shape psi suppression was discovered within months of the paper, already with light ion beams, only to be undiscovered a few years later when it was found that this was more likely a nuclear matter effect rather than a Quark-Gluon plasma effect. Luckily, to be rediscovered again a few years later with heavy ion beams. And so it rested till we switched on RIC. And to everybody's surprise, the suppression, the difference to 1 at RIC, was identical to the suppression at SPS. And that was completely unexpected, ununderstood, because RIC has a much higher density, a much higher temperature, so it should suppress the shape psi much more. So much for the well-calibrated smoking gun. The puzzle was finally solved at LHC when we found that the suppression, the difference from 1, is actually less strong than at RIC. So there are actually more shape psis, properly normalized, which survive at LHC than at RIC. Again, that was a complete surprise to everybody except those who believed in regeneration. And what seems to be happening is that when we put the shape psi in the Quark-Gluon plasma, it happily melts, it diffuses. But at high energies, there are so many charm quarks and anti-charm quarks in the plasma that by the time the plasma has cooled and has hadronized, ever once in a while, one of these charm quarks will find an anti-charm, and you will have a resurrected shape psi, regeneration. Now, happily, this effect, this regeneration, is as good a deconfinement signal as the original melting, because deconfinement actually means color conductivity. The quarks can freely roam over large distances, and that's, of course, what they have to do to go from one place to another and reunite with a completely independently produced charm quark. Actually, we could have probably known that we would find something weird with the shape psi. After all, we were trying to make the shape psi disappear using Sam's magnet, and that couldn't work. Okay, let's now see how we measure the properties of this dense matter, and this we do with a phenomena mainly which we call hydrodynamic flow. You all have an intuitive impression what flow is. Particles which are close by in space, they go in the same direction with the same velocity. And flow in general develops in every medium where you do have pressure gradients and interactions, and it's described in the framework of hydrodynamics. So there are two things which define how the flow develops. One is the initial conditions. These are the geometrical boundary conditions and the pressure gradients. In this case, the initial conditions are the fire hose and the pump. And then, of course, the fluid properties, like the equation of state and the viscosity. So we're interested in the latter, that's the Quark-Gluon plasma properties, and we have to know the former. So how does flow develop in heavy ion collisions? You have such a off-center collision. The overlap zone has a deformation. It has this elliptic almond shape. And that means the gradient in the short direction is larger than in the long direction. And that then leads to differential expansion, stronger in plane than out of plane. And this in turn then leads to an azimuthal distribution of particles, which shows this very strong modulation. So flow is driven by eccentricity. The more elongated, the more pressure gradient, and it's damped by viscosity. What you see is that this modulation, this elliptic flow as it's called, is actually very large. There are 3 times more particles in plane in this direction than out of plane, so something you cannot really miss. And this very strong modulation was the reason to call this Quark-Gluon plasma an ideal liquid, one which has essentially 0 viscosity. So what does it mean, 0 viscosity? Actually, what we measure is not viscosity. We measure viscosity over entropy, or we calculate viscosity over entropy. This becomes then dimensionless. Now, viscosity is inversely related to the cross-section. So small viscosity means large cross-section, means a strongly interacting fluid. The value which was extracted from the data at RIG at the time was of order eta over s of order 1. Actually, it was an upper limit. It was not a value. So it was not 0, but it was a small number, and it is particularly small if you compare to other good, well-known liquids. For example, this is the viscosity over entropy of superfluid helium. And very surprisingly, the Quark-Gluon plasma is a better liquid than even superfluid helium here at the lambda point at 4.2 Kelvin. Even more interesting, the value is of the order of 1 over 4 pi, which is the number which has been conjectured by this ADF-CFT calculations to be the absolute lower limit for any quantum fluid. That is actually reached when the mean free path is of order of the wavelength, not the Compton wavelength, of course, but of order of the de Broglie wavelength. So how good is now the liquid really? We only had initially an upper limit. For this, we had to realize that our smooth approximation of the overlap zone is not really good enough. Nuclei are composite objects. They have nucleon, and so there are fluctuations. And these fluctuations not only have elliptical shape, they also have triangular shape. In fact, they have any shape. You can Fourier decompose these initial conditions. You find Fourier components of any order. And these are very important because they actually give us a much better handle on the viscosity. This is shown here. You have one of these lumpy initial conditions, so that's one heavy ion collisions with fluctuating energy deposits. We transport that in hydro with an ideal liquid for about 6 Fermi over C. That's what I call the lifetime of the plasma. You see that the stuff sort of squishes out, it flows away. This is now for an ideal liquid with 0 viscosity, and this is how it looks like for the same initial collision with some finite viscosity, 2 over 4 pi. And you see that it's much more fluid, it's much more damped, and in particular the spiky structures, the higher Fourier components are damped more. And that's of course well known in physics. We call it acoustic damping. We find that in many fluids and many media, including in the early universe. So we measure today not only this elliptic flow, the second order component, we can measure it all the way up to 5, 6, even 7th order. And by looking at the acoustic damping, the relative ratio of these flow amplitudes, we have now reached an accuracy that we know after about 10 years that the viscosity is not only an upper bound, it's actually a value, and it's not 0, it's at least 1 and maybe 2 times this quantum limit of 1 over 4 pi. So not an ideal liquid, but still a rather good one. Okay, let's now look at some of the properties we measure with another effect, which is called jet quenching. If you have a hard scattering, you have jets, and if you embed these jets in heavy ion collisions, the jets have to traverse, at least one of them has to traverse the matter, and then it can lose energy by radiation or collision. That's actually a process which was calculated by BJ, I don't know whether he's still here, in the early 80s. He calculated only one part, namely the collisional, but later on it was shown also to be radiative. And this energy loss depends on one property of the Quark-Gluon plasma, essentially the opacity, the radiation length of the Quark-Gluon plasma. And this is what we want to measure, but it also depends on the length, of course, and maybe to some non-trivial power, depending on the theory and the process. It depends obviously on the color charge, whether you are quark or gluon. It does depend on the mass via quantum interference effects, and it does depend on the energy. So that's actually a very rich signal. We can measure not only how much energy is lost, but also dynamically where it is lost, where it reappears. Energy, even in heavy ion collisions, is conserved. And we can also check the expected scaling. So jet quenching was seen again right after the switch on of RIC. It was seen in the suppression of fleeting hadrons, of high PT hadrons, which is shown here. You find only about 20% of what you expect, whereas photons, which couple weakly to the plasma, are not suppressed. So we got our normalizations right. At LHC, it's a very spectacular phenomena. There are many more unbalanced jets than in PP, and we even find, finally, the monojets in heavy ion collisions. So with this phenomena, by studying the balance of jets, we can measure this Q hat, this opacity of the quark-gluon plasma, with about 30% accuracy. If you translate that, that amounts to a typical energy loss of 10 to 20 GeV in the quark-gluon plasma. Now that's a big number. It means you could stop the beam of the PS, for example, over the size of one nucleon. So that's a big number. But we have also measured, for example, that heavy quarks lose less energy than light quarks, light meaning charm. We have studied the energy flow inside the jet cone by looking at fragmentation functions, both transverse and longitudinal. And we have seen that the radiated energy appears at very large radii, really at the edge of the cone in very soft radiation, in very soft particles. So we could study that really in great detail and measure the properties of this quark-gluon plasma, which again is very strongly interacting, strongly absorbing. So let me come finally to the surprise. And that, in fact, was the first discovery at the LHC, which was made already in the first year of operation in September. And it was seen in PP collisions, actually, at very high multiplicity in the two-particle correlation functions. So this shows the two-particle correlation functions as a function of azimuth angle and of rapidity. These are the well-known structures from the near-side jet, from the away-side jet. And then there was this very difficult, actually, to see initially small bump, which extends over very, very large rapidity ranges, 8 units of rapidity. This is called the ridge. And it was so unexpected that Diego Tonelli, who was the spokesperson of CMS at the time, when he announced this to a packed auditorium at CERN, he said, "We're here today because we didn't succeed to kill this phenomena, and we want to expose our finding to the scrutiny of the community." Now, those of you who have followed neutrino physics know this as the opera defense. Actually, this time it did work. The effect survived, and it spawned a very, very large number of different explanations, rather ad hoc, speculative, and most of them actually outright weird. 2 of them still stand today. One is an initial state effect, which is related to this color glass condensate. So it has to do with the initial wave function of the proton, which before it collides. And it would require actually, again, yet another new state of matter, now this time a dense and cold parton matter state in the initial state. And the other possible explanation is that this effect is similar to the flow I discussed before, which of course is much, much stronger, much more visible in heavy ions, but it does look roughly similar. So we still are not at the end of this debate today. However, we have studied light ions, PP and PA, almost as well by now as we have studied heavy ions. This was not the idea, but after the first results came out, we looked in detail. And it turns out we found essentially all the quark-gluon plasma signals we have ever looked and wanted and loved in AA. We have seen them in one form or another, also in proton-proton and proton-nucleus collisions. With one noticeable exception, the jet quenching has not yet been identified. And not only we have seen them, for example, even other quark-gluon plasma signals like strangeness enhancement. This shows here the omega to pi ratio from PP, low multiplicity, high multiplicity. It rises continuously till it reaches a plateau in lead-lead collision. And it really goes down to minimum bias proton-proton collisions. So this has led really to a rethinking of our field. We were used to thinking that hot matter is created only in heavy ion collisions, in big objects, like shown here by this ink drawing, which was commissioned by T.D. Lee, again at the beginning of heavy ion physics, of nuclei as heavy as bulls through collision generate new state of matter. That was our paradigm at the beginning. And we thought proton nucleus is only useful to measure nuclear matter effects, like the one which obscured the shape psi. And PB is really somebody else's problem. That's high energy physics. We don't want to know how that happens. And now we have seen that there is really a deep connection. We seem to be finding the same QGP-like signals everywhere. So clearly, this has led to some rethinking. It's not yet at the end. We don't really know how this is related, whether it's actually related. My personal take on that is that all these collective signals, all these Quark-Gluon Plasma-like signals, are not really a unique property of heavy ion collisions. They are rather a generic property of all strongly interacting many-body systems. So 2 is company, and 3 or more is a collective crowd. Even our high-energy physics colleagues have taken note. You see here one recent preprint by no less than Sjöstrand, the author of Pythia, who, in context with these results, has written that the understanding of soft hadronic physics is changing at the LHC. And to him, at least, it seems that many of the most unexpected new LHC observations may well be in the low PT region than in the high PT one. That reminds me of, I think it was yesterday, Jurgen, who said there are the planned discoveries, like the Higgs, and there are the unplanned discoveries. And that definitely is what we have seen in the strong interaction sector at low PT. So let me come to the end. We set out 30 years ago to find a weakly interacting ideal gas of quarks at gluon. What we have found instead is this almost perfect, strongly interacting liquid, a macroscopic piece of matter with rather amazing properties, which we can experimentally measure in quite an exquisite detail and follow its evolution by looking at various signals. So we have measured some of its properties. I mentioned the viscosity or the opacity, but also other coefficients with quite some detail. We have good evidence of deconfinement. We have some, admittedly, indirect evidence of chiral symmetry restoration. And we know that the relevant degrees of freedoms are actually not weakly interacting quarks and gluons. The interaction is way too strong. So what have we learned? As yesterday David said, we expand our sphere of knowledge and in this process find an increasing interface with ignorance. So again, also in our case, we have more questions now than we had at the beginning, and prime is what are actually the relevant degrees of freedom? Are these pseudoparticles? Are these quasi-particles? Are these collective excitations? We have no clue. What is the dynamics? We know perfectly well the thermodynamics. We know the statistical properties, but we haven't looked under the hood. What is really happening in the Quark-Gluon plasma in terms of dynamics? And finally, where is the onset? The idea was we would find it with heavy ions, and we find it wherever we look. So how do these phenomena emerge from small systems with increasing energy density and increasing particles system size? So we have learned a lot about the how, but we really don't understand much of the why. So that leaves really plenty to do for the future. And if I have another 2 minutes, which I have, I will tell you about the immediate short-term future. On the high energy frontier, we will be running with heavy ions, I think essentially as long as the LHC will be running, even in the high luminosity phase, in order to make increased precision measurements with rarer and rarer probes, including, for example, photon-jet correlations. And also in particular to address some of these why questions. Again, David yesterday mentioned the Rutherford scattering experiment. And actually, our dream is to do a Rutherford scattering experiment to scatter the partons of the degrees of freedom of the Quark-Gluon plasma. And if they come back at large angles, we actually have some resolution to find what they are. And in particular, to study more the onset, how this develops in small systems, including PP. And for that, at the LHC, we will increase the luminosity also at heavy ions by a modest factor, and in particular, upgrade the detectors. And also at RIC, the physics will go on, in particular at the high energy frontier with a new detector, which will measure also now better the jet quenching phenomena with jets at RIC. There's a second frontier which we haven't really discussed at all. I've concentrated on the axis of zero net baryon density, the axis of the early universe, but there's also the density axis when you compress matter, and that has to be addressed at lower energies. Now, there are reasons to believe, while we know here it is a continuous transition, that here it may actually be a first-order phase transition. And if that's correct, it has to end in a critical point. And locating this critical point and measuring the properties along this axis is the aim of a number of low-energy machines, a beam energy scan at RIG, so where you lower the energy rather than increasing it. It continues at the SPS in the fixed target program, and there are 2 new accelerators currently being built, one in Dubna, which should come online in about 3 years from now, and another one at GSI around the same time scale, maybe a few years later. And even at JPark, there are ideas to use fixed target experiments to study this high density axis of the phase diagram. So we have learned a lot of key answers deep inside. We have found big surprises as actually expected. It's a still very active program. About 15% of the LHC, actually of the people physicists, is doing heavy ion physics rather than PP physics. And we are looking forward for another, maybe not 30 years, but let's say 10 or 20 of a very competitive program, in particular at the high baryon density region. Thank you very much.
In this phase diagram, can you in principle imagine overheating or undercooling so that you move in the diagram but you still sit in the wrong phase?
Yes, so there were ideas, of course, to see whether we have critical phenomena. Now the problem is a little bit that at this axis it's continuous. So while it is still steep, it's not clear whether you would find really critical phenomena or bubbles. On the other hand, if there is a critical point, then we actually should see it, because then correlation lengths should diverge. Even in finite system, we should see effects. So here we are looking now especially for fluctuations in baryon number, in conserved quantities, and they could be indicative of some overheating or supercooling. There are other more speculative ideas which are related to particle production, but I think our best bet is if there is a critical point, that's where we could maybe find these critical phenomena. And of course, that would be very relevant and welcome to study, as we heard in the talk yesterday about the early universe. If there are critical phenomena at higher energies, of course, then they might have some implications for the baryogenesis, not the QCD phase transition, but still it would be nice to study this phenomena in a quantum field theory in an actual experiment.
Seeing that you see these effects, by, as you say, by surprise in PP as well, in many cases, I wonder, is there stuff you can learn from deep inelastic scattering? Can you connect this to low X,
yes.
high density QCD?
Yes, and actually the first attempts have been done. Now, in this color glass framework, it is actually related, and the people are very proud that because they use parameters from HERA, for example, to fix their free parameters, the alpha exponent of the saturation momentum, for example. But actually what we have done now is something even more interesting. We have looked at archived lab data and at archived electron-positron data. And the first result I've heard 2 weeks ago at Quark Matter. And lo and behold, in E plus E minus, we don't find these phenomena. And also in EP, we don't find them. After some thinking, it probably has to do with initial conditions. I mean, if you have something which is round, it's S-channel annihilation E plus E minus. And if it's round without structure, then you don't see these. Then the initial conditions will not give you this fluctuation in the flow. And maybe something similar happens in EP. But that's so fresh that's really hot off the press. But what is interesting is that we can use the archive data. I think it was Aleph data, in fact, to revisit things which nobody would have thought of at the time of lab, and actually get results out. So finally, archiving and making the data available does seem to be useful.
On your future, I don't see the analog of what you do at the LHC for the FCCHH.
So there is, of course, I only wanted to cover my lifespan, and so I stopped at the end of the LHC. But there is, of course, also for FCC, the younger generations are heavily discussing what to do. And for example, one beautiful example would be regeneration. If we get up with more charm quarks, you should see shape psi enhancement at the FCC. That would be a beautiful demonstration of this new process of generating, of reviving the shape psi. But they are also looking at many other things, even including top physics, that you can hadronize a top in the Quark-Gluon Plasma. So there is a ongoing study. And again, I'm sure if the FCC HH will be built, it will become a collider of large hadrons like the LHC.
One exciting thing is that at ERIC or at electron-ion collider is actually you can see the ridge effect in electron-ion collisions. And what's interesting is the electron plane, scattering plane, controls the ridge. That's because of angular momentum consideration. So you can actually, and that occurs if in fact the collision happens when the two flux tubes collide and break each other up, then there's a correlation with the angles.
Yeah. So in particular, if the ridge, this is not my opinion, but if the ridge indeed is related to this initial state, to the color glass condensate, to this gluon wall, then this really opens a very, very rich field for ERIC, because that's then a precision machine to study this initial state.
I can't resist saying one more thing, by the way, and that is that you showed a graph where a figure where the heavy ion is contracted to a pancake. Penrose and Weisskopf showed that's fallacious. That happens if you violate causality and so on.
This is the question I usually ask my students: what's wrong with that picture?
Yeah. In fact, if you're in a spaceship and you're moving fast, you're not contracted to death.
These were the initial baryons, and they, however, contracted.
No,
so
they
it's
do
only
not.
the wee hadrons which are not.
No, there's no contraction. A particle does not change its state just because it's moving. And this is, when you use front form, Dirac's front form, you get it correct because it's causal. If you use instant form, then you're looking at the state at one instant of time, and you're not doing that. That violates causality. So in fact, there is no such phenomena. And in fact, everything in high energy physics would be wrong if you had contraction. Structure functions are not changed just because the proton is moving. The state is exactly the same no matter what the momentum is. So I think this is, it's a common misconception, but it goes all the way back to Penrose and Weisskopf that they had it right.
Still, you do have relativistic dilution, so the shape size, for example, hadronize outside, and that is still true.
Oh, that's something else. I'm talking about the initial condition.
Okay.
Yeah, okay.
Forgive me if you said this and I missed it, but I've been learning from my friends about ridges in ultra-peripheral collisions. Are they the same ridges? Are they related ridges? Are they at all relevant to the high baryon density frontier?
I must have missed those. I mean, there are some phenomena in ultra peripheral, like photon nucleus, Pomeroy nucleus collisions, but I don't think we have seen a ridge. The ridge is this phenomena of two particle correlations, and I don't think we have seen that we've seen other interesting phenomena in ultra peripheral collisions, but I'm not aware of a ridge. I'm not aware.
All right.